Kepler's first law of planetary motion says that planets orbit an ellipse. And so I don't want to derive this expression, which I may do later. Instead, I want to show this relationship. So we can model the motion of a planet orbiting the sun numerically in Python, and then we can show that its path is an ellipse. Okay, so what is the equation of ellipse? So let me explain this law. It says that if there's a sun, and this is a planet orbiting the sun in a non-circular orbit, but a circle is an ellipse, okay, then it orbits in a path like this, where the sun is at one of the foci. I don't know, that seems like a weird word, the foci. And that's that, right? So that's what it says. You know, if you think about it, this is really crazy, because Kepler looked at the stars and the planets and mapped the motion of, not only did he map the motion of the planets as seen from the Earth, which is also orbiting the sun, but then he said, well, look, I think that they all have to have this elliptical orbit, which, I mean, some of these aren't very elliptical at all, or they're very circular. So you have to get good data to show this is true. And it's a crazy thing. And then when Newton came along, he showed that it was true. But it's, you know, there's no physics here. It's just, it's an ellipse. Okay? And that's the way we start off a lot of times. Just, this works. Okay, so how are we going to model this? So I'm not going to draw an ellipse. Instead, let's start with the sun. And I'm going to actually put the sun at the origin for now. If I have a planet right here, and there is a vector location with respect to the sun of r, then there is a gravitational force pulling on the planet this way, F. I'll just call it F. And the magnitude, actually not just the magnitude, we can say F is negative g, big M, little m, mass of the sun, mass of the planet, over the distance between them squared, which is the magnitude of the vector, r hat. So what do you do with that? I can calculate the gravitational force at any particular location, right? Over here, it'd be smaller because it's further away and so forth. But how do you model the motion of that? Well, now I'm going to use the momentum principle along with this. So the momentum principle says that if that's the only force, the net force on an object, F, is the change in momentum with respect to time. And I've written this as a finite difference because of what I'm going to do. So momentum is mass times velocity. So I need to know the velocity of this. I'm going to start off with a planet on the x-axis moving in the y-axis, right? Just because it's going to make it an ellipse where the two foci are on the x-axis by doing that. And you could imagine the x and y-axis aren't real anyway, so you could always pick a system such that that's true by choosing appropriate x and y-axis. So how do I do this? Because this force is pulling this way, but the momentum's that way. Well, that's going to make it turn, but it's also going to move to a new location, so I'm going to have a new force. So this turns out to be a non-trivial problem, not unsolvable. We can solve this in a lot of different ways, but it's really fun to solve numerically. So if you haven't solved a problem numerically, I'm going to step you through the whole process because I think it's useful. Okay, so here is the planet at some location. It has a momentum. We're going to break this into short time intervals. I'm just going to say short, right? Small time intervals. And so if you're talking about planetary motion, that can be a large time interval, in terms of days or whatever, or hours. So I'm just going to say short for right now. It has some momentum P1, and it has some R vector and an F on it. During that time interval, I can assume the force is constant, which it's not. So assume F is constant. And see, that's my favorite joke. A vector has to be equal to a vector, so it's a constant vector. If that's the case, then I can say F is P2 minus P1 over delta t. It's just the change in momentum. So this is the momentum at the end of the time interval over here, P2, and that's at the beginning. So if I know the momentum at the beginning, I can find the momentum at the end. I can say, well, I can first calculate F. So let's write that out. F is negative G M over R1 squared R1 hat. So this is the vector position at that location right there. That's R1. Then I can calculate P2 by multiplying by delta T and adding P1. So I get P2 is P1 plus F delta T. So I can update the momentum over that time interval assuming F is constant, which it's not. But if delta T is small, it's kind of true. Then I can say the same thing about velocity. I can say the velocity is P over M, which is equal to delta R over delta T. And again, if I assume velocity is constant over this time interval, which it totally is not, but kind of totally is, then this, I can write this as R2 minus R1 over delta T. And I can solve for R2. So I get R2 equals R1 plus P2 over M delta T. So I put P2 here because I just calculated, updated the momentum. I'm saying I'm using momentum at the end of the time interval. It turns out that works better numerically. And then I'm going to update time. T2 equals T1 plus T. I'm going to show you something in just a second. And then I'm going to go back up here and repeat the whole thing. And this is the Euler method of numerical calculations. It's kind of a big deal. It's very simple. It works very well with a small time interval, and it's a lot of work if I want to do a whole bunch of these, but that's why we have a computer. So I can program this into Python, and Python even deals with vectors, and I can model the motion of this planet. So just to be clear, I don't want to use all the fancy values of the mass of the sun and the mass of the planet. So I'm just going to say G, just for now, because I'm just trying to show that it's an ellipse. G is 1. That's the gravitational constant right here. The mass of the sun is 1. The mass of the planet is, guess, 1. And now that's bad right there because that assumes that if those are both the same mass, then the sun would move. But I'm going to assume the sun doesn't move. Okay, so this works. Kepler's first law, I don't think it works. I'm not sure now. Maybe it does. It's kind of true. Maybe there's a modified version for if the sun moves too. I'm going to start this position off over here at 1 on the x-axis with a velocity of, I think, 0.7 this way, meters per second. So totally whacked out. And then I can use a delta t of 0.001, which may or may not. This could be some unit of systems that it works, right? Okay, let's jump right into it. I'm going to go over to Python. I'm going to get an orbit of the sun, and then we can go back and make that we can make it show that it's an ellipse. Okay, so here we are on the computer. So I'm using web vpython, and this is in trinket.io, and I will give you the code, okay, so you don't have to write it down. So let's just get started. So I'm going to start typing in some stuff here, all my constants. G equals 1, M equals 1, lowercase m equals 1, R1, that's where it starts, is 1, and then V1 equals 0.7. And so you have to be careful because depending on how you make that ellipse, and you'll see that some of the things I'm going to use to determine the parameters of the equation won't quite work. So just be careful with that. The great thing about Web vPython is it has these three-dimensional objects. So I can make the sun a three-dimensional object. Sun is a sphere. Position is equal to, let's put it at the origin, vector 0, 0, 0. And let's say the radius is 0.03 and color is yellow. And let's run that. It's always good to run it after you do something like that. And something bad. Oh, there it is. Okay, there's my sun, and I can rotate it around. I can zoom in and out. It's really nice. If you haven't played with this, it's really fun. Okay, now I'm going to make my planet. Planet is also a sphere. Its position is going to be equal to, I'm going to say sun.pos plus vector r100, right? So sun.pos is the vector location of the sun. And I'm adding on to it, shifting it over a distance r1, so we'll be on the x-axis. I'm going to make it a little bit smaller. Radius equals 0.01. I'm going to give it color cyan, color dot that shows up well with a black background. And I'm going to do this, make trail equals true. Now let's run this. So there's that's my star, the sun, and that's a planet right there. You can see it right there. Okay, I guess we should save this. Kepler's first law demo. I'm not proving it. I'm just showing that it's true. Okay, now I need to give the planet an initial momentum. Planet.p is going to be equal to m, its mass, times the vector 0v10, right? Because I want to have an upward velocity in the positive y direction of v1. Next, I need a time of 0, dt of 0.001. That turns out to be fine. And let's just make it move. So I'm going to say while t less than 3. I don't even know. I'm just picking something. While t is less than 3. So it's going to keep on doing this loop until t gets to 3. So that means I need to have a t equals t plus dt. That's going to update time. If you don't put that, then this will run forever, and that's just awkward. Rate 1000. So rate tells Python to not do more than 1,000 loops every second. Since I have a time step of 1/1000th, this would take 3 seconds to run. Okay, so now the first thing I need to do is to calculate the vector r, right? So r is the vector from the sun to the planet. So I'm going to say r is planet.pos minus sun.pos. So if you draw a vector from the sun to the planet, yes, since the sun's at the origin, this should just be the planet.pos. But I like to do this because what if the sun moved or something, then this code would still work. That's why. Okay, so now I can calculate the gravitational force. F equals negative g times m times norm r. So norm is a built-in Python function that returns the unit vector in the direction of r. If you don't have that in your equation, then you just have a scalar value for the force, and this will not work. You have to have a vector. And then I'm going to divide by mag r, so squared. So mag is a function that returns the magnitude of a vector. And so I want the magnitude of the vector and then squared. And so star is raised to the power in Python, in case you didn't know. Okay, so now I have the force. I can update the momentum. So planet.p equals planet.p plus f times dt. So in Python and in most programming languages, is this big enough? Maybe I should make it a little bit bigger. This says take the vector value of the momentum and then add this f times dt to it. And then make that the momentum. So I don't have to worry about 1, 2, 3, 4 momentums. I can just change the momentum. Now we can do the same thing for the position, which is the position of the planet, planet.pos, planet.p, plus planet.p, POS, planet.p times dt divided by m. So that updates the position. And the update time. That's it. Let's run this. See if we get an orbit. I mean, that looks pretty good. Okay. So it didn't finish. We didn't go long enough. Let's just change this to 5 and run it. So it looks elliptical, but we definitely want to see if it is fully elliptical. So I need to make some measurements. And my problem here is that the equation of an ellipse, I would need this as my center. So I need to find this distance, right, across here. That distance is going to be 2a. This distance is going to be 2b. So if I know those distances, I can find that. And I want to do something that makes sense. So here's what I'm going to do. I'm going to make these points. I'm going to call it A1, A2, B1, and B2. So A1 right there, A2 over there. And I need to move them. So I'm going to make these points. And this point, A1, I started at that point. I just knew that one. And B1, the point up here, what's true? What's true for this point up here? Number one, the velocity goes from in the positive y direction to the negative y direction. So I want to look for the very, very, very small y velocity. And I want x, and I want y to be positive, right? Because that would be up here. Because down here, the velocity is very small too, but y is negative. So I can distinguish between B1 and B2 based on those two conditions. Very small y velocity and positive y value, negative y value. And then I can, the same thing over here, I can find this because there's a very, very small x velocity and a negative x value. Okay, so let's make these points. I'm going to make them how big? 0.02, just so you can see them. And let's make them red and blue. So let's make the points. So I'm going to say A1 equals sphere, position equals planet.pos. It's going to start in the same spot. Okay, that's where I'm going to start it. And it has a radius of 0.01 and a color of red. Color equals color.red. It doesn't have to be, but. And then I'm going to make A2, same thing. A2 is the same thing. And then I'm going to make B2, B1, and I'm just going to change this to B. And I'm going to change this to blue. And then I'm going to copy that. And then I'm going to make B2. So they all start in the same spot. They all start at the starting location. And I'm only going to move it when the conditions are met for that thing. And I'm not going to get it exactly in the right position. I'm just going to be kind of close. Okay. So I'm going to put this after I've updated everything. So I need to find where am I going to put B1. So I'm going to say this. If planet.pos.y is greater than 0, right? I have to have it up there. And the momentum is in the y direction is very, very small. But how small is small? Instead of using the actual momentum, I'm going to use the unit vector for the momentum. Because then I know it has a maximum value of 1. So I'm going to say, and what am I going to say? ABS for absolute value, norm planet.p, that's going to give me the unit vector between -1 and 1 for the total y component, but then I'm going to say .y, right? So that's the y component. And then ABS says, I don't care if it's going up or down, I just want it super small. Because there's going to be a range over there. And let's just put this as less than 0.01. And you could play around with this if you want, but that number, if you make it too small, then it's a numerical calculation that's jumping around. It could actually jump over that criteria and miss it altogether. But if that meets that criteria, then I'm going to move B1 to that location. So I'm going to say B1.pos equals planet.pos because the planet's moving. Okay, so let's see if that works. Let's just see if it moves that dot just for that first one. So let's just try it out. Okay, see, there it is. See? Do you see that blue dot? Maybe I should make it a little bit bigger. Let's make these 0.2. So it looks like it did work. So there's the dot. There's the other one right there. Okay. So now I just need to do the same thing for A2 and B2. So down here, I'm just going to copy this. Let's just do, oops. That's fine. Backspace that. If planet.pos is less than 0, so it's -y, and it's that way, same thing. This is just for B2. And then I can do it for A2. I'm going to say if planet.pos.x is less than 0, and planet.p.x is less than 0.1, then A1.A2. Okay, so this should put all the values there. Okay, there's B1, there's A2, and see, you notice that one turned red because I had the blue dot over there, but now it looks like that looks pretty good. I'm pretty happy. Now we can do some calculations. So let's calculate down here. After the loop, I want to calculate A. So A is going to be that distance between those two A points divided by 2. So I can say A is equal to the magnitude of A2.pos minus A1.pos divided by 2, right? Because a, that's going to be twice a from that distance. So I'll take the distance between them, divide by 2, and I should get a. And the same thing for b. B is going to be mag b2.pos minus b1.pos divided by 2. And then I can also calculate c. Did I put c on my picture over here? Yeah, c is the distance from, assuming that my ellipse is centered at the origin, it's the distance from the focus to the origin. So, but that's also equal to a minus the distance the thing starts from the object, right? Because I start at a distance r1. If I subtract off that a, then I'll have c. Does that make sense? Okay. So c is equal to a1.pos.x. That's the, or I could just do a. No, I need the actual location. a1.pos.x minus a. Right, so that's the x component of the first point minus the actual value of a, and that gives me the location from the origin to the focus, which I will need. In fact, I could put another sun at the other focal point, the foci. It's not a focal point, it's a foci. Sun 2 is equal to a sphere. Position equals vector. It's going to be twice that distance, right? Because I have the sun at one origin, so I need to go to the origin, the new origin, and then one more c. So it's going to be 2 times c, 0, 0, and let's give it a radius of 0.03, and let's run that. Let's see if it looks right. Nice. Okay, so I'm going to make a graph of an ellipse. So let's just go ahead and I want to plot this trajectory, and then I will add on a graph of the ellipse, and it should be the same thing. And that way we can see they're the same thing. So I'm going to add a graph up here. So I'm going to put it at the top, G1 equals graph, X title equals X, Y title equals Y, width, no, you got to spell it right, width equals 500, let's do height equals 500, but it's going to, let's do 300. It doesn't really, it's not going to work out perfectly anyway, so I don't really care. Now I need a graph. I'm going to graph F1 equals G curve, color equals, if you have questions about graphing, just let me know. I can go over as many graphing stuff as you want. Color.blue. So this makes, G1 makes the axis. F1 is the thing I'm actually plotting. So down here, I'm going to plot F1.plot. I want to plot the trajectory, so X versus Y. So that's going to be planet.pos.x, planet.pos.y. Okay, so there's my trajectory, and it's doing it in the loop. So there's my ellipse, and it's squished. It doesn't look perfect because the vertical and the horizontal axes aren't scaled the same. It's close, but there you go. Now I need to draw another ellipse. I'm going to calculate an ellipse. So we actually need to do a quick calculation. So let's jump back over to the paper. My paper's stuck. Okay. So I know my starting value of x. And I know this is the equation of ellipse. X squared over a squared plus y squared over b squared equals 1. There's more than one way to graph an ellipse. But what I'm going to do is to solve this for y. So let's subtract this from both sides. I get y squared over b squared equals 1 minus x squared over a squared. Now I'm going to take the square root of both sides. So I can say y over b is the square root of 1 minus x squared over a squared. And now I'll multiply both sides by b, and I get y equals b square root of 1 minus x squared over a squared. So now if imagine I'm plotting something, I'm starting here at this certain value of x, and I can calculate y. If x is 0, y should be 0, right? 0, well, if x is 0, no, x is not 0. That's right over here. Okay. So x is some value. X is some value such that y is 0, but it doesn't really matter. Now I'm going to decrease my value of x. I'm going to plot y. I'm going to decrease my value of x over here and find the new point, and I get it right there. Decrease it again, find my new point, decrease, find my new point, and that will give this. But I don't have the bottom part of the curve because I'm not plotting it. I'm not making a trajectory. I'm plotting x and y. So what I need is two y's. I need a y plus and then a y minus is going to be that when I take the square root, I get plus or minus. So I'm going to say negative b square root of 1 minus x squared over a squared. And I'm going to plot both those at the same time, and it'll look like that. Okay, so I actually need two curves. I need a y plus and a y minus. So let's make two curves and another loop and go through and calculate these values. And it's not going to work because I know you may know why, but that's fine. So going back to the code, I'm going to make two more curves. I'm going to make them red. So let's say F2 is G curve, color equals color dot red, and then F3 equals G curve, color equals color dot red. I want it both to be red. Okay. So now I'm going to make another loop. I'm going to go over here. What's my starting value of x? So I'm going to say x equals r1. I want to start it at that same spot, right? Because I want to make the trajectories match. And then I need a dx. How far am I going to step? I have an exact calculation. I don't need this too small. I'm going to say 0.01. So next I can say while x is greater than, I want to go all the way to that last point, which is a2. a2.pos.x, right? So I want to decrease the value of x until it gets to the other end of the ellipse. Then I will say I need to calculate my y. So I'm going to say yp, the plus y, is going to be equal to b times the square root of 1 minus x squared divided by a squared. And then I need to calculate my negative one. Ym is negative b times square root 1 minus x squared over a squared. Now I'm going to plot both those. So I'm going to say f2 dot plot x yp, f3 dot plot x ym. And then I need to change my value of x. X equals x minus dx. And I feel like I might have made a mistake, so let's save this and run it. Did it save? Okay, run. Okay, so it does the orbit. You know, you got to make sure you get down here to get all the points. There's that graph and then the other graph. Okay, but you'll notice that I did those calculations based on the wrong center. So I need to shift everything over. So let's just shift over my red ellipse. It looks like it's working. Let's just shift over my red ellipse. So I need to shift it over by amount c. So I'm going to go down here. I'm going to say xp for the plotting x is x minus c. And then so every time I change x, that's going to change. And this is going to be xp now, right? Yeah, xp squared, xp. And then I'm going to plot just xp, just x. Yeah. So there it did that. And then something happened. Oh, there it did it. Okay. Right on top of it. Identical. So in this particular case, that is an equation of ellipse, and it matches the trajectory of the planet. So the planet does move in an ellipse. Kepler's first law is demonstrated to be true, did not prove it to be true. Okay? Code down below. That's all I have to say.